All right, guys, so welcome back. And what we'll do for this hour is we'll look at some examples of some of the things that we've talked about here. So I'm trying to do an example that compares the comparable versus comparator method for sorting and comparing things and stuff like that. So we'll see if this works out. I'm going to do this after we talk about some of the other stuff first. Okay. So if we run out of time, I'll do it next week. All right. So here is the array list and linked list example. Okay. All right. So we're going to create an array list, and I like doing this with the canvas here so that you can see it kind of visually. What happens here. So this array list thing, I'm going to show you what this looks like. Okay, so after we put that in there. Now remember what I said was the underlying data structure underneath the array list is an array, and that's why it looks like this in the visualization. Let me expand this a little bit. That's why it looks like this with this contiguous. Remember this continuous memory location. So memory location 0, memory location 1. So when we add a new item to here, we're going to add it to the next memory location. Same thing again, right? So here we have 1, 2, 3, 1, 4. Now we're going to add something at this location 0, the value of 10. So what that means is that we want to put this 10 here, but we don't want to lose anything that we already have. So that's the big difference here. That's the big difference between the way that we might do this with an array, where we might say array at index 0 equals 10, is we're going to take 10 and we're going to put it in here. And one thing I want you to notice is that notice that all of these values are red. The reason for that is because in this visualization, it's showing you everything that had to change. Because the way that this happened, the way that the add method for the array list functions, is it took the 4 that was here and it copied the value over to here first. So it took 4 and put it into here. Then it took 1 and put it into here. Then 3 and put it into here. Then 2 and put it into here. Then 1 and put it into here. And then finally put the 10 in here after it had moved everything else forward. A lot of work, right? So it would be like if you had boxes of stuff, right? And you wanted to put something in the first box, but in order to do that, you had to get everything that was in that first box into the second box. But before you could do that, you had to get everything that was in, and you're actually looking at me like this. So you had to get everything in that second box into the third box. And then before you could do that, you'd have to get everything out of the third box into the fourth one. Well, and as someone who's done this, putting kids' toys away, it can get very, very frustrating, right, and annoying. It takes a long time. But to take everything that's in that second to last box, the last box that has stuff in it, and dump it into the last box, then take the next one, dump it, then take the next one, dump it, then take the next one, dump it, and then finally put whatever it is into that first now empty box. Okay, that's why all these things are red, is they're showing you everything that's changed. And the reason why I want to point that out is because then when we do this next step, we're going to put at index 3 the value 30. Notice that now only these have changed. All of this stayed the same. Nothing changed here. We moved this forward, we moved this forward, moved this forward, and then we put this value in that place. Okay, and then we can display a list of integers in the array list. And then we can just print the array list. It will call what method? What method of the array list? The list here. What method is it going to call? We can take a look. There's a priority queue example here we can take a look at. We'll look at that one in just a moment. Yep. But as far as the array list part, the toString method, yep. So the toString method kind of on brackets on each side gives me all of my values in the array list or in the list, all right, in order. Okay. Now we're going to create a linked list that's based on the array list. And I'm going to do this thing again. Where are you? Not browse. There it is. My linked list. Because I want you to see how this looks different. And yet, in some ways, it might look the same, but it's also very different. Okay. So notice, first things first. Let's notice. The order's all the same, right? 10, 1, 2, 30, 3, 1, 4. Right. But something's different. What's up with all these extra little boxes everywhere and everything? Why is all these rectangles here? Okay, so the way that a linked list works, and actually when you get to your algorithms and data structures class in the future, you'll learn that this is actually what's called a doubly linked list. That's why the arrows go both directions. Okay, but let's just talk about this from the perspective of a linked list. Okay, so let's just talk about just these top set of arrows only. Okay, so we have a pointer to the first node in our list, to the first item in our list. But every item has a pointer to the next item in the list. So this points to this one. 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 So forth. Okay. If you want to think about it like this, let me pull up a new Java, imagine if you had a something like this, where you had a list, linked list, and you might have. Now, by the way, I don't know the implementation of linked lists. I've not studied it, so this may or may not be it. Okay, so don't take my word for this. This is not the way Java does this. More than likely, there's probably a lot going on in here that I don't know about. Okay, but you have some private object, we'll call it value. Okay, and what this part of the linked list is, this part of the node, we'll actually call it linked list node. Okay, so this is this node here. One part of it is the value. The other part of it is the next node in the next node in the list. Okay. So 10 points to this node, which has a value of 1, which points to this node, which has a value of 2, and so forth, and so forth, and so forth, until you get to, and I'm going to ask you this question, this node that has a value of 1, its next, the next node is this one that has the value of 4. What do you think is the next value for this node? So its value is 4. What do you think the next linked list node is? Right. The way that we know that we've reached the end of the list is if our current one points to null. Okay? If this points to null, there's nothing else. There's nothing else after. We're done. Okay. Now, what's probably confusing some of you guys with the one thing, I think you're thinking about it pointing back to here. That's what's called a doubly linked list, and basically the difference between a doubly linked list and a single linked list. that a doubly linked list has two. Okay, 2 pointers. One that points to the next node in the list, one that points to the previous node in the list. There's a reason for why we do doubly linked lists instead of just one linked list, but that's for your algorithms and data structures course. I don't want to get into that too much here. Okay. All right. So, but the last node here, and by the way, for the doubly linked list here, one thing I will say is that this one's previous also points to null. Okay. So we can start at the first thing in the list, right? And we can go through the list item by item until we get to some node that points to null. Once we reach the point at which our node points to null, we're done. No more linked list. We're finished. Okay. All right. So let's go back over to this to see what happens. So now we want to add something at item 1. Okay, at index 1. So just like we did with 10 here, where we put 10 in at the index 0, we want to put something in at index 1. Okay. So we want to put it here between 10 and 1. How many red things are going to pop up? Is it going to be 1, 2, 3, 4, 5, 6, and then the one we're entering, 7? Is it going to be just the one that we're entering? This is going to be fun, okay? Get ready to watch. Okay, watch the animation over here. Okay, now it is blue in the sense that like it moved it a little bit and it's green. I don't know. Jay Grass likes doing all kinds of things in different colors, I guess. I don't know. But notice that what it did was it moved all that stuff along. But notice that all the pointers stayed the same, didn't they? We didn't have to change anything about the pointers. We didn't have to change what 1 pointed to. We didn't have to change what 2 pointed to. We didn't have to change what 3 and 30 and the other 1. We didn't have to change any of those pointers. The only thing we had to do was we took 10. It was pointing to 1. And we simply said, take 10 and point it to this new thing, red. Take red and point it to what 10 used to point at, 1. Take 1 for the reverse. Take 1 and point it to red. Take red and point it at what 1 used to point at, 10. Okay. The reason why, and I'm excited about this, but I'm also, this is stuff I love, right? But this is the fact that we didn't have to go through all the work of copy this over, copy this over, copy this over, copy this. This would be like, again, going back to my putting my children's toys away in different boxes and different bins example, right? This would be like the difference between me saying, okay, these boxes are stationary. All right, these boxes are stationary, and what I want to do is I want to take, well, there's all this stuff in all these boxes, but I want what's in the first box to be his Legos, okay, his Lego sets. But right now, he's got his Star Wars lightsabers in there. But I want to keep the same order of what he's got on all the boxes. So an array example or an array list example, the solution would be take what's in that last box and dump it into the next empty box. And then keep going down the line, right? And then once that first box is empty, we can put whatever other toy, which, what other toys do my kids play with? Stuffed animals, stuffies. They call them stuffies, stuffed animals, right? So those are all going in that first box, okay? That would be the array, dump, 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 put, right? That would be the array solution. The linked list solution, however, I don't know. I'm pointing at my screen. I don't know what you guys are seeing me point at. But the linked list example, however, says, oh, you want your stuffies in the first box? Okay, well, what we'll do is we'll just put it there. And we're done. No dumping, no moving, just done. Just put it there. Everything else kind of slides over. Done. No dumping, no copying, no nothing. Right? It's a much simpler solution, right? Hopefully my kids pick up on this, that they can do this way. Right? In the same way, let's say we wanted to remove an item from the array list. Let's say we wanted to remove 2 from the array list. What do we remove? Well, let's say we wanted to remove 2 from the array list. Okay. We would have to take it out and we'd have to move everything else forward, right? Or I guess you're looking at it this way. So we take 2 out and move everything else forward. There's a lot of extra work, right? Whereas to remove an individual linked list value, a linked list node, 2, for example, here, this guy here, we simply take this one before it, point it over to here, take this one after it, point it over to here, and 2's gone. Nothing points to 2 anymore. No copying, no moving stuff around, none of that. All right, a lot easier. And so what we'll see is as we remove the last, right, it just goes, it's just gone. Right, just took 1 and pointed it to null, and we're done. Okay. We want to add first green, so we want to add something here in the first position. Let's see what's going to happen. Right. So we just took green, pointed it at what was the first thing, and took the head of our list and pointed it to our new node green. Okay. So then we can also display the linked list backward by going from the linked list size down to 0. So we'll see what happens there. All this stuff backwards over here, you'll see that. 10 and green. And is that it? Yep, that's it. So we can display it based on size backwards. Okay, now there's a trade-off. There's always a trade-off in these things, because I'm sitting here and one of the things that you keep hearing me say is how great the linked list is, and look, oh, we can just change the pointers and we're done. We don't have to copy stuff over and all this stuff. Okay, but there's an old principle. I'm going to write it here. This is an old principle, okay? Okay, we call it the Tan-Staffel principle, and I'll type out what it stands for. Okay, look it up sometime. There ain't no such thing as a free lunch. And what it means is that there's always a trade-off. It means that just because one thing is better in some regards than another doesn't mean that it's always better. There's always going to be, or often, there's often going to be something that we have to give up in order to get the benefit of whatever the better thing is. So think about it this way. So in this example where we're comparing the linked list and the array list, okay, the linked list for inserting values and removing values was very fast, right? We didn't have to copy stuff over, we didn't have to move stuff around, we simply did some pointer changing, right? We changed what the node pointed at, or well, in both cases, I guess we changed what the nodes pointed at and we were done. We didn't have to copy values into different positions. Okay? But searching based on index is much better with an array list. Okay? So if you wanted to say, I want to know what is in, so look at this index, look at this array list up here. If I said, what is the value in index 4? You could tell me very quickly, right? If I had an array list here that was a size of 100 elements, and I said, can you tell me what is in index 98? You could tell me very quickly, right? You would just do it. You'd be like, 98, got it, done. Okay, you say, shh, 98, done, right? Here, what's the value at index 6? Well, 0, 1, 2, 3, 4, 5, 6. Okay, so 6 right here. Right? That's how a linked list has to do it. Right? Unfortunately, a linked list does not have quick access to the index the way that an array list does, because an array list, remember, it's contiguous memory locations. Right? It's one after the other. They're all contiguous, which means if I wanted to look at a particular index, I just do a quick math thing and say, let me just get that index 6 or 7 or 103 or whatever. With a linked list, to find the thing at a certain index, I have to start at index 0. I have to start at the first item in the list and move that many places along. Look at the next, 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 until I get to whatever index I'm looking for. Okay. So linked list for inserting, for removing values, very fast compared to array list. For searching, for finding out what is a value, what's an element at a certain position in my list, an array list is a much faster data structure. Okay. All right. So that's how that all works. Let me see here. Let me move out of here. Let's see. You wanted to know about the priority queue. Right, so the way that a priority queue works. What was your question? Let me see if I can find it. What do you mean by one operation? I'm a little bit confused there. So I don't think they're necessarily making a lot of use out of the priority part of the priority queue here, because I'm not really sure why this is different from a queue and a priority queue. Oh, they're doing it as a heap, basically. Okay, so they're doing it. So I guess Georgia. Why is Georgia first? So Georgia's first. Okay. Oh, so they did this as, okay, they did this as a heap style structure. Okay. So they're doing, priority is basically by alphabetical. So you see you're doing Georgia, Indiana, Oklahoma, and then Texas will end. And then this uses a comparator here. So if I want to see what Q2 looks like. Interesting. Yeah. Yeah, so a Q, the way that the Q would normally look. Yeah, so what, let me go ahead and get rid of this. So to understand why they're formatting it this way, Arjun, to understand why Canvas is showing it the way that they are, you'd have to understand heaps, which is well kind of outside of the realm of this class. It's more of a data structures and algorithms class, again, that you'll learn there. But quickly, let me just explain the way that the priority queue for strings seems to be operating is it's kind of like a sorting. And so you'll see here, we put it in Oklahoma, Indiana, Georgia, Texas, but where's my output? Right here. Okay. But Georgia, Indiana, Oklahoma, Texas came out in that order, which isn't the same order that it went in. So basically what it did was it said, we're going to put, so the way that it puts priority is based on alphabetical. So Georgia came in and went ahead of Indiana and Oklahoma. Right? Texas comes in and goes at the very end. Okay. So if there was a way to say have two different values that were both equal, so if you go back to my hospital example, my emergency room example, if two people came in with maybe different problems, one has they've cut their finger, the other maybe has, cut something else, cut their hand, or maybe has like a sprained finger or sprained bone, a sprained ankle or something, then those might be considered as the same level of priority. And so at that point, if two things come in at different times with the same level of priority, then the priority queue becomes a first in, first out structure. Okay. So we put priority to the priority things first, and then everything that's at the same level of priority gets serviced first in, first out. Okay. I hope that's kind of clear there. All right. So I want to do the comparable. I don't think we're going to have time to do my example here. I don't think we're going to have time for my example. So let's instead talk about this comparator. Let's just look at a comparator example on its own. Okay. That's geometric object comparator. Let's just compare. Okay. So it's going to make me take this chapter 13 stuff, isn't it? Is it going to work? Oh, maybe it will. Oh, good. Yay. Okay. All right. So remember back when we were talking about the comparable interface, and we had this whole geometric object that was comparable. In fact, I can pull it back up. It was a comparable rectangle, for example. Remember, we had this comparable rectangle that extends rectangle, that implements the comparable interface. And what we had was inside of this comparable rectangle class, because it implements this interface, right, we needed to have this compare to method. And basically what we said was if my get area is greater than the get area of the object that's being passed to me, then return 1. Otherwise, return if my get area is less than the area of the thing being passed to me, then return -1, and otherwise return 0. Okay. And do we have a test comparable? Sort comparable objects. Right. And so these things that implement the comparable interface, we can sort them. Right. We can sort these things that implement the comparable interface. Does this one do it? That's something else. That's not what I want. All right. So anything that implements the comparable interface, we can sort them using the arrays sort method. We also noticed, you may have noticed also that the collections interface had a sort method as well. Okay. All right. So that was one way, was to take the class itself, implement the comparable interface, and inside of the class have this method, this override method for compare to. That's one way to be able to sort things, to be able to put them in order. Okay. Let's talk about this other one, this comparator. Okay. Now, let's imagine the geometric object, which we're going to go look at what it looks like. No. Here, this. Okay. This geometric object, notice it does not implement the comparable interface. Right? So on its own, geometric object is not a comparable object. We cannot compare one geometric object to another on its own. But we can create a comparator. Where are you? Where are you? There you are. Okay. We can create a comparator class, right, that implements the comparator interface for geometric objects. Don't worry about this serializable part over here. Okay, that's something else. Okay, so we can create this all separate comparator class that what it will do, it will have a compare method. Now make sure you know the difference. It's a compare method, not the compare to method. Okay, the comparable interface has the compare to method. The comparator interface has the compare method. I know. Why didn't they just name it the same thing? Well, there's reasons. Okay, but what's going to happen is we're going to take two objects. The compare method is going to take two objects that we want to compare to each other. If area 1 is less than area 2, we return -1. If area 1 is equal to area 2, we return 0. Otherwise, we return 1. Okay, now, basically, okay, -1, it doesn't have to be -1. +1, it doesn't have to be +1. All that it has to be is, in order for the first object to be considered whatever less than is, whatever we want to call less than. Okay, if O1 is less than O2, we return a negative number. We want this method to return a negative number. If whatever is O1 is, we would consider it greater than O2, we return a positive number. If whatever O1 is, we want to have it seen as equal to whatever O2 is, then we want to return 0. It's the only one that we have to return an exact value. We have to return 0 if they're equal. We can return any negative number if it's less than, any positive number if it's greater than, but it has to be 0 if they're equal. Okay. And we can change what does it mean for something to be less than, greater than, equal to. For example, if I were to pull up OBS right now, and if I were to look at this class for grades, hopefully you guys saw, I went ahead and posted the midterm grades. I don't know if you saw those or not. And all of you stopped listening to me and you're rushing over to OBS right now. So we'll close out in just a minute. But so if I pull up OBS and I pulled up this class, I could sort you all by student ID. That's how it defaults, actually. When I first pull up any screen involving this class or any class for that matter, the first view I get is all of the students sorted by student ID. So whoever has the lowest student number, you're first in my list. And whoever has the highest student number, you're last in my list to start with. But you know, when I want to go through and like look for somebody to maybe change a grade if I've realized if they've brought to my attention that I didn't grade properly or whatever, which does happen, you know, student number isn't really how I want to search for you, is it? No. So up at the top they have the little linkable titles, the little titles that are links, right? And what happens is if I click on it, it sorts by whatever column I've clicked on. So if I click on your first name, it'll sort. Well, suddenly how students compare, what one is considered greater than another, is different, isn't it? Before, it compared you based on student number. Now it's going to compare you based on first name. I could click on grade, like if I wanted to find out who the highest and the lowest grades in the class were, very quickly, I could click on the grade link, the column. And what would happen is it would sort based on grade value. And so how you would be compared to other students would be based on this grade value. And so what's happening in a much fancier and a much more complex way than what we're looking at here is the criteria for negative, 0, and positive is changing because we're using something else in there that's not just, we're using something else in there that's not, excuse me. We're using something else in there that's was student number, now it's student name, now it's grade, now it's whatever, right? So what defines less than, equal, and greater than may change over time or may change based on usage. Right? And we can do that using either the comparable or the comparator. The big difference here, the big usefulness here is the comparable interface. If we go with the comparable interface, we have to change the class for the object itself. So like student, in this case, whatever. I would have to change the student class itself because it has that compare to method from the comparable interface. Whereas this methodology, what I get is I have this extra class, this comparator class, right, that I have to use in order to make it happen. I don't change the geometric object class. I don't change the student class. I can change it here instead. I can change it in the comparator itself. The problem is where the trade-off is. So the benefit of the comparator is that if the conditions for what's considered less than, equal, and greater changes, I can change it here. I don't have to change it in the main class itself, in the object itself, right? But the downside is that also means that, say for example, the max method. If geometric object if it implemented the comparable interface, I wouldn't need all this stuff here, right? I could just be like, done, right? If geometric object implemented the comparable interface, Max could just take the 2 and be done. I don't have to add anything else to it. But because it does not implement the comparable interface, I have to add to the Max method, I have to add this geometric object comparator instead. Okay. All right. All right. And the same is true for like the sorting, for example. So here, where are you? Where are you? I guess, oh, here, sort. Anything that implements the comparable interface, I can just put it in, I can put an array or an array list or a linked list of that into the sort method and I'm done. Don't have to add anything else. If it doesn't implement the comparable interface, I'll have to add a comparator to the sort method to be able to allow them to sort. Because without that, without either the object type itself being an instance of comparable or without adding a special comparator, the sort method has no understanding of how to compare the two to each other, of how to compare any two items to each other. Okay, so 2 different ways. One, make the class itself implement the comparable interface and make the compare to method, or the other option, is to create a comparator class that implements the comparator method, comparator interface, and create a compare method for it. Okay, either one will work. Okay, just one way does it one way, one day does it the other. Okay, 2 different ways that we can kind of get the similar results here. All right. Okay, so we'll end there for today unless there are any questions. Okay, yeah, okay, I see you're asking. Now, Arjun, I'm finally getting around to the first question where you said that I read the Canvas part, but yeah, the priority queue, like I said, you really, in order to understand the way that it shows it in the Canvas, you really have to understand what a heap is. Yeah. So for those of you who have had your algorithms class already or your data structures class already, then you should know what a heap is. Okay. All right. Are there any questions before we dismiss? Okay. Well, we'll end for today there. I'll see you guys in a week. And like I said, what I'll have is next week I will have my my tablet with me so that I can draw, so that I can kind of show you even more kind of visually what's going on with all the stuff with array list and linked list and stuff like that. Okay. All right. Thanks, guys. Have a good weekend, and I'll see you in 1 week.